place là con này con bị dính place. Ôi giời ơi, tắt quá. Học sinh chạy thùng cái đơn nhỏ nhỏ giờ
ơi.
Dạ.
Em gửi anh là để coi connection. Cái role này role là cho cái gì vậy ta? Role là cho cái này em nói là cái tắt với cái self với cái distinct hai đúng không?
Dạ. Cái role của thành collection nó
là để mình insert cái tắt đó gì?
dạ.
Insert tắt insert cái seller với insert hai rồi. Còn cái update là để cho edit đó đúng không? Update collection rule.
Collection rule là cho nó giống với insert luôn.
Giống với insert nhưng mà để cho update data đúng không? Edit đó hả?
Dạ.
Add collection. Rồi nha.
Anh nghĩ anh nhớ cái tag product là anh sẽ phải truyền hết những cái tag mới nha, tức là nó sẽ xóa hết cái cũ và nó mới, cho nên anh sẽ truyền luôn cả những cái nào. Là sao? Tức là nếu mà anh muốn thêm một cái tag mới vô tag product á, ví dụ nó có một cái tag A thì anh muốn thêm một tag B thì anh sẽ truyền cái tag IDS là của cả A lẫn B.
Ok, hiểu rồi. Lúc mà update á hả? Lúc mà product.
Dạ đúng rồi.
Còn nếu anh xóa thì anh cứ, nói chung là anh chỉ cần kêu là product tag product rồi anh chỉ pass lại một cái list tất cả những tag mới, còn những cái tag nào không có tag không phải mà anh xóa thì nó tự động xóa thôi.
Dạ.
Ok.
Ok, Thuận ơi, bao nhiêu đó chắc là đủ để làm cái collection trên server dashboard rồi. Còn ở bên buyer seller view thì chắc là sẽ cần nhiều hơn, tại vì nó có một số cái nhỏ.
Tại vì đúng là anh, tại vì vô cái recommend nó biết cái cần thiết, em nghĩ là đủ rồi, nhưng mà chắc là sẽ phát sinh cái nhỏ
đó. Mình đó giống như là nó sắp xếp thứ tự của cái collection để nó show ở trên cái buyer view nữa, rồi nó có thể toggle cái vụ mà nó có thể một cái section nó có feature, nó có show cái feature section này không?
Dạ.
Rồi cái gì nữa ta? Bên ngoài thì nó có cái nhỏ. Ok, dùng nó tính sao đi.
The serial queue that handles the database operations. The reason for this is twofold. Firstly, by dispatching the work onto a different queue, we ensure that the main thread can remain responsive to user input, even while waiting for a potentially we need to first dig into how threads are brought up to handle work on GCD queues. In Grand Central Dispatch, when work is enqueued onto a queue, the system will bring up a thread to service that work item. Since a concurrent queue can handle multiple work items at once, the system will bring up several threads until we have saturated all the CPU cores. However, if a thread blocks, as seen on the first CPU core here, and there is more work to be done on the concurrent queue, GCD will bring up more threads to drain the remaining work items. The reason for this is twofold. Firstly, by giving your process another thread, we are able to ensure that each core continues to have a thread that executes work at any given time. This gives your applications a good continuing level of concurrency. Secondly, the blocked thread may be waiting on a resource, like a semaphore, before it can make further progress. The new thread that is brought up to continue working on the queue may be able to help unblock the resource that is being waited on by the first thread. So now that we understand a bit more about thread bring-ups in GCD, let's go back and look at the CPU execution of the code from our news app. On a 2-core device, like the Apple Watch, GCD will first bring up 2 threads to process the feed update results. As the threads block on accessing the database queue, more threads are created to continue working on the networking queue. The CPU then has to context switch between different threads processing the networking results, as indicated by the white vertical lines between the various threads. This means that in our news application, we could easily end up with a very large number of threads. If the user has 100 feeds that need to be updated, then each of those URL data tasks will have a completion block on the concurrent queue when the network request is complete. GCD will bring up more threads when each of the callbacks block on the database queue, resulting in the application having lots of threads. Now you might ask, what's so bad about having a lot of threads in our application? Having a lot of threads in our application means that the system is overcommitted with more threads than we have CPU cores. Consider an iPhone with 6 CPU cores. If our news application has 100 feed updates that need to be processed, this means that we have overcommitted the iPhone with 16 times more threads than cores. This is the phenomenon we call thread explosion. Some of our previous WWDC talks have gone into further detail on the risks associated with this, including the possibility of deadlocks in your application. Thread explosion also comes with memory and scheduling overhead that may not be immediately obvious. So let's look into this further. Looking back at our news application, each of the blocked threads is holding onto valuable memory and resources while waiting to run again. Each blocked thread has a stack and associated kernel data structures to track the thread. Some of these threads may be holding onto locks, which other threads that are running might need. This is a large number of resources and memory to be holding onto for threads that are not making progress. There is also greater scheduling overhead as a result of thread explosion. As new threads are brought up, the CPU needs to perform a full thread context switch in order to switch away from the old thread to start executing the new thread. As the blocked threads become runnable again, the scheduler will have to time share the threads on the CPU so that they are all able to make forward progress. Now, time sharing of threads is fine if that happens a few times. That is the power of concurrency. But when there is thread explosion, having to time share hundreds of threads on a device with limited cores can lead to excessive context switching. The scheduling latencies of these threads outweigh the amount of useful work they would do, therefore resulting in the CPU running less efficiently as well. As we've seen so far, it is easy to miss some of these nuances about threading hygiene when writing applications with GCD queues, thereby resulting in poor performance and greater overhead. Building on this experience, Swift has taken a different approach when designing concurrency into the language. We've built Swift concurrency with performance and efficiency in mind as well, so that your apps can enjoy controlled, structured, and safe concurrency. With Swift, we want to change the execution model of apps from the following model, which has lots of threads and context switches, to this. Here, you see that we have just 2 threads executing on our 2 core system, and there are no thread context switches. All of our blocked threads go away, and instead, we have a lightweight object known as a continuation to track the resumption of work. When threads execute work under Swift concurrency, they switch between continuations instead of performing a full thread context switch. This means that we now only pay the cost of a function call instead. So the runtime behavior that we want for Swift concurrency, when threads execute work under Swift concurrency, they switch between continuations instead of performing a full thread.
Không truyền lên thôi.
Không truyền lên lại
Không truyền lên.
Thằng Apollo tự lo rồi, có nghĩa là nếu anh truyền luôn ở dưới file nó tự bypass qua, nó không truyền về trong cái hash.
Nhưng mà anh để không có trong cái anh không để cái parameter đó nó cũng chết nè.
Đâu? Không, trên Hasura trên này thì đâu của anh đâu. Không, ở trên này thì không được, nhưng mà ở dưới cái iOS của anh thì thằng Hasura đã làm chuyện đó rồi.
Cũng không được luôn, tức là cái param của anh nó không có cái marketplace, anh bỏ nó qua nó nè, cái param của anh không có.
Anh bỏ cái bằng nôn ở trên được không?
Bỏ bằng nôn để trên đi chị ơi.
Bỏ luôn nè.
Rồi.
Cũng không được luôn.
Expected name null mutation. Cái display name gì có vấn đề kìa.
Display name gì có vấn đề.
Không, nó chọn ngay chỉ như nó display name kìa, syntax euro gì cũng kìa, syntax euro rap kia về cái con đây là có vấn đề.
Anh xóa cái display name này đi, anh xóa thằng này đi. Còn lại phần display name thôi. Bình thường.
Đang xem lại thử em.
Xem lại bình thường nè.
Xem lại. Cái marketplace anh này dưới anh không có thì nó báo rồi.
Thì bây giờ để bằng vô để coi như
một khoảng trời pha giữa mây đen lân tiếng ngôi sao tên em bức tranh còn vương chút sầu anh vẽ trong làn khói muôn màu từng cho anh nếm hết đắng cay mà anh những ngày say vô tư đi theo em chẳng biết lý do gì lại ngất nơi bao đầu này bay trong đêm đêm được nhìn thấy thứ lấp lánh của anh trôi bên lời vừa khóc vừa cười cùng ngã vì người đoạn đường xa biệt vừa chẳng thấy lòng dép giữa cái nắng hoa hương so beautiful so beautiful so beautiful a beautiful murder em như con tiên đang là lướt xanh cả tiên anh chỉ biết nhìn theo đến quê không ngừng dây em nghĩ mình đúng phải buộc anh theo cuộc chơi vậy ngày mai có chuyến tàu này sẽ đi đến bao giờ rời khi đôi tay đang ghi thật chặt con
Cost of a function call instead. So the runtime behavior that we want for Swift concurrency is to create only as many threads as there are CPU cores, and for threads to be able to cheaply and efficiently switch between work items when they are blocked. We want you to be able to write straight-line code that is easy to reason about and also gives you safe, controlled concurrency. In order to achieve this behavior that we are after, the operating system needs a runtime contract that threads will not block. And that is only possible if the language is able to provide us with that. Swift's concurrency model and the semantics around it have therefore been designed with this goal in mind. To that end, I'd like to dive into two of Swift's language-level features that enable us to maintain a contract with the runtime. The first comes from the semantics of await, and the second from the tracking
Có
of
khi
task
là nó
dependencies in the
không phải là
Swift
nó không
runtime.
phải là bị lỗi cái đó đâu anh.
Là gì?
Từ để em cho.
Cả cuốn khôi.
Nó bị zero chứ không phải. Có nghĩa là nó trả về cái error message á, chứ không phải là trả về cái instant text set đâu.
Trả về error message. Ok. Ủa nhưng mà vậy
Mấy không mà kiểu cũng vậy à. Nó cái pass nó error biết à.
cũng được luôn.
Cái đó không lẽ đi.
Lạ lắm, nó bị báo nó error biết à. Rồi nha, để thử cái trường hợp là
Đúng rồi. Ồ, Win rồi. Hello.
Let's consider these language features in the context of our example news application. This is the code snippet we walked through earlier that handles the results of our newsfeed updates. Let's see what this logic looks like when written with Swift concurrency primitives instead. We'd first start with creating an async implementation of our helper function. Then, instead of handling the results of our networking requests on a concurrent dispatch queue, here we are using a task group instead to manage our concurrency. In the task group, we will create child tasks for each feed that needs to be updated. Each child task will perform a download from the feed's URL using the shared URL session. It will then deserialize the results of the download, format them into articles, and finally, we will call an async function to update our database. Here, when calling any async functions, we annotate it with an await keyword. From the meet async await in Swift talk, we learned that an await is an asynchronous wait. That is, it does not block the current thread while waiting for results from the async function. Instead, the function may be suspended, and the thread will be freed up to execute other tasks. How does this happen? How does one give up a thread? My colleague Varun will now shed light on what is done under the hood in the Swift run child task because it does not our database. Here, when calling any async functions, we annotate it with an await keyword. From the meet async await in Swift talk, we learned that an await is an asynchronous wait. That is, it does not block the current thread while waiting for results from the async function. Instead, the function may be suspended, and the thread will be freed up to execute other tasks. How does this happen? How does one give up a thread? My colleague Varun will now shed light on what is done under the hood in the Swift runtime to make this possible.
Thanks, Rohini. Before jumping into how async functions are implemented, let's do a quick refresher on how non-async functions work. Every thread in a running program has one stack, which it uses to store state for function calls. Let's focus on one thread for now. When the thread executes a function call, a new frame is pushed onto its stack. This newly created stack frame can be used by the function to store local variables, return address, and any other information that is needed. Once the function finishes executing and returns, its stack frame is popped. Now let's consider async functions. Suppose that a thread called an add method on the feed type from the update database function. At this stage, the most recent stack frame will be for add. The stack frame stores local variables that do not need to be available across a suspension point. The body of add has one suspension point, marked by a weight. Local variables ID and article are immediately used in the body of the for loop after being defined, without any suspension points in between. So they will be stored in the stack frame. Additionally, there will be two async frames on the heap, one for update database and one for add. Async frames store information that does need to be available across suspension points. Notice that the new articles argument is defined before await, but needs to be available after the await. This means that the async frame for add will keep track of new articles. Suppose the thread continues executing. When the save function starts executing, the stack frame for add is replaced by a stack frame for save. Instead of adding new stack frames, the topmost stack frame is replaced, since any variables that will be needed in the future will already have been stored in the list of async frames. The save function also gains an async frame for its use. While the articles are being saved to the database, it would be better if the thread could do some useful work instead of being blocked. Suppose the execution of the save function is suspended, and the thread is reused to do some other useful work instead of being blocked. What the fuck? Stored in the list of async frames. The save function also gains an async frame for its use. While the articles are being saved to the database, it would be better if the thread could do some useful work instead of being blocked. Suppose the execution of the save function is suspended, and the thread is reused to do some other useful work instead of being blocked. Since all information that is maintained across a suspension point is stored on the heap, it can be used to continue execution at a later stage. This list of async frames is the runtime representation of a continuation. See after, since all information that is maintained across a suspension point is stored on the heap, it can be used to continue execution at a later stage. This list of async frames is the runtime representation of a continuation. While the articles are being saved to the database, it would be better if the thread could do some useful work instead of being blocked. Suppose the execution of the save function is suspended, and the thread is reused to do some other useful work instead of being blocked. Since all information that is maintained across a suspension point is stored on the heap, it can be used to continue execution at a later stage. This list of async frames is the runtime representation of a continuation. See after a little while, the database request is complete, and suppose some thread is freed up. This could be the same thread as before, or it could be a different thread. Suppose the save function resumes executing on this thread. One database request is complete, and suppose some thread is freed up. This could be the same thread as before, or it could be a different thread. Suppose the save function resumes executing on this thread. Once it finishes executing and returns some IDs, then the stack frame for save will again be replaced by a stack frame for add. After executing and return some IDs, then the stack frame for save will again be replaced by a stack frame for add. After that, the thread can start executing zip. Zipping two arrays is a non-async operation, so it will create a new stack frame. Since Swift continues to use the operating system stack, both async and non-async Swift code can efficiently call into C and Objective-C. Moreover, C and Objective-C code can continue efficiently calling non-async Swift code. Once the zip function finishes, its stack frame will be popped, and execution will continue. So far, once the zip function finishes, its stack frame will be popped, and execution will continue. and non-async Swift code can if stack frame for save will again be replaced by a stack frame for add. After that, the thread can start executing zip. Zipping two arrays is a non-async operation, so it will create a new stack frame. Since Swift continues to use the operating system stack, both async and non-async Swift code can efficiently call into C and Objective-C. Moreover, C and Objective-C code can continue efficiently calling non-async Swift code. Once the zip function finishes, its stack frame will be popped, and execution will continue. So far, I've described how await is designed to ensure efficient suspension and resumption, while freeing up a thread's resources to do other work. Next, Rohini will describe the second language feature, which is the runtime tracking of dependencies between tasks.
Thanks, Varun. As described earlier, a function can be broken up into continuations at an await, also known as a potential suspension point. In this case, the URL session data task is the async function, and the remaining work after it is the continuation. The continuation can only be executed after the async function is completed. This is a dependency tracked by the Swift concurrency runtime. Similarly, within the task group, a parent task may create several child tasks, and each of those child tasks needs to complete before a parent task can proceed. This is a dependency that is expressed in your code by the scope of the task group, and therefore explicitly known to the Swift compiler and runtime. In Swift, tasks can only await other tasks that are known to the Swift runtime, be it continuations or child tasks. Therefore, code when structured with Swift's concurrency primitives provide the runtime with a clear understanding of the dependency chain between the tasks. So far, you've learned how Swift's language features allow a task to be suspended during an await. Instead, the executing thread is able to reason about task dependencies and pick up a different task instead. This means that code written with Swift concurrency can maintain a runtime contract that threads are always able to make forward progress. We have taken advantage of this runtime contract to build integrated OS support for Swift concurrency. This is in the form of a new cooperative thread pool to back Swift concurrency as the default executor. Runtime contract that threads are always able to can proceed as there are
compared to other forms of mutual exclusion. Consider the earlier example of updating the database with some articles by syncing to a serial queue. If the queue is not already running, we say that there is no contention. In this case, the calling thread is reused to execute the new work item on the queue without any context switch. Instead, if the serial queue is already running, the queue is set to be under contention. In this situation, the calling thread is blocked. This blocking behavior is what triggered thread explosion, as Rohini described earlier in the talk.
non nun. Breaks. Của đôi này không có hủy cái offer đúng không?
Sao ta? Đang bắt đầu làm thì đi vô đi muốn coi, xong rồi coi hỏi đi muốn làm seller cái bắt đầu đang chuẩn bị demo thì có dùng mấy chiếc comment đó, xong đi kêu là đi bắt ra 15 phút, xong cái sổ ra luôn. Em kêu em feedback tiếp khi nào cần thì
Cũng nhiều có thể có giờ làm tôi thấy chắc là bên đó chắc là hôm nay không nói đâu, bên này bên đó đang bận cái canh giữ mấy cái Black Friday đơn nhiều. Đầu cơ đi đố biết vài cái chơi
để em coi.
Kiếm mấy cái đơn dưới 5 đô còn kiếm, toàn có 5-6 đô nhiều, tại một cái 1 đô biết mấy cái này lên tụi nó mới kích lên. Anh có đang nói không? Biết đây không để anh biết luôn.
Anh biết luôn ngay.
Có một
em đang kích
lên 1 đô biết cái nữa chơi 2 đô đi. Mấy 2 đô vẫn thua.
Nó cả đã biết đúng không? Anh không biết.
Tôi biết rồi. Bạn vài đô tháng, ok. Rồi. Được. 422 4 CPU lên cao vãi. Hết đợt chiều này auction chắc anh phải nâng cái con server lên thôi, chứ không thì nguy hiểm quá. Chết ngắt ra mùi sống hết. Của cái view cao của anh Hòn xong rồi sao mà kêu hôm nay deploy anh?
Cái vụ nuôi cao mới nhớ là làm web nữa.
Cái đấy anh deploy cái Node.js app production này.
Staging với lại bổ sung khác nhau đúng không? Hai cái khác nhau đúng không?
Hôm qua mới đang chạy staging. Deploy server trước.
Mấy cái database mình có thời điểm nó lên 70% CPU, hơn 70. Anh không biết là tại sao.
Pháp sư làm nhạc. ngọn đèn và trời hôm nay gió lặng tim đen.